Hey everyone, in this video we're going to discuss a few PID implementation issues, and we're going to discuss 3 strategies to solve some common problems. The content of this lecture comes from Chapter 14 of Chemical and Bioprocess Control, 4th edition by James Riggs. So in this lecture we're going to discuss the following 3 topics. Okay, the first is what's called Anti-reset Windup. So Anti-reset Windup is a strategy, it's a strategy to prevent an accumulated error in the integral term from causing your system to overcorrect. The second strategy is called Bumpless Transfer. So Bumpless Transfer is used to help with things like startup and set point changes to prevent the process from behaving a little crazy. And the third method or third strategy is what's called split flow control. And split flow control is an approach that can be used to achieve a wider range of flow rates that you can achieve with a single valve, or to do things like heating and cooling simultaneously within a system. So the objective of this lecture is to be able to discuss what these 3 strategies are and how they're implemented to solve current problems or to solve common problems associated with some feedback control loops. Okay, so we're going to start with reset windup. So reset windup is something that can occur for PID controllers. And this occurs when something won't allow the controller to eliminate the error from the set point. Okay, so this can be caused by things like valve saturation. So in a working PID feedback control loop, your control valve can become fully open or fully closed. And once that happens, you can no longer eliminate the offset by further opening or further closing the valve. There's things that we discussed previously that are called override select. Okay, so override select is, there could be a safety or process constraint loop that's overriding the primary feedback control loop. And if this occurs, there will be a sustained error between the set point and the control variable. And whenever you have a sustained error between the set point and the control variable, this error will accumulate once the limitation goes away, so once this limitation goes away, the accumulated error will cause the system to overcorrect because the valve will remain open, and the point of the integral term is to make the overall accumulated error from the time that the process started equal to 0. So as you accumulate this, assume maybe you're accumulating positive error when you have something like valve saturation or override select. Once this term goes away, we need to accumulate negative error in the opposite direction in order for the effect of the integral action term to go back down to 0. Okay, so the most common reasons for windup, so this is what's called windup. Windup is this accumulated error in the integral term. So the most common reason for this is valve saturation, as we said. So the large disturbance in the set point causes the control valve, so it causes your control valve to swing fully open or fully closed. And when your valve is fully open or fully closed, no more control can be achieved. Okay, so let's see why this causes only problems with the integral term and not for the rest of the term. And I'm going to write up here. So if you can recall, when we do process control, or we look at feedback controllers, the PID control algorithm, all of these terms, or all of the functions, are in terms of deviation variables, which are changes from steady state values. So the controller output's not going to be an actual controller position, or an air pressure signal, or a valve position, but it's going to be a change. So change in valve position, change in air pressure, etc. So the output from the controller is a delta. So if we look at the digital form of the PID algorithm, it's going to look like Kc, which is the gain term. So then we have first our proportional term, which is Et minus E, so the error at the current time minus the error at the previous time. Now recall, if we have valve saturation, or if we have this error that's a sustained error between your control variable and your set point, these error terms will be equal, so the effect of the proportional term will be 0 on the requested change by the controller. If we look at the integral term, so this is going to be plus delta t, the time integral over which the DCS makes the measurement, over tau I, which is the reset time, times the error at the current time. Okay, so if you have a sustained error, this term right here is always it will be non-zero. So this term right here, at every time period in which a change is requested, this term is going to accumulate. It's going to add to the delta C, which wants the system to make a change further away from what it currently is. And then we also have the derivative term, which is the derivative time constant times the error at the current time minus 2 times the error at the previous time plus the error at 2 time intervals ago, all over 2. So again, this is the digital version of the derivative of the error. Again, if you have a sustained error, all of these terms will be approximately equal to each other. So this term will be 0, and so the effect of the integral action is going to cause an accumulation with this change in controller output, which is going to cause the controller to overcorrect. And again, because this term is going to be non-zero for sustained oscillation, in order to get the system to get back down to the set point, in order to eliminate this accumulated error, you have to have an opposite sign on this error for the same time period. So your positive error deviation needs to be equal to your negative error deviation in order for this accumulated error to go away. Here's what it looks like graphically. Okay, so shown here is when you have a system that allows for reset windup, it's going to look like this. So on this chart, on this plot, we have our set point, which is shown here. So no change in the set point. And there is something that disrupts the system. So for example, it could be an override select loop, or maybe the valve's all the way open or all the way closed due to a large disturbance. So what happens is now we have this sustained offset because we have valve saturation or override select. Our control variable is now less than the set point. So we have this error that accumulates, and so for this time period we have this accumulated error. Once the constraint or once the disturbance goes away, what happens is the system is going to, again, the controller during this time period, the controller is trying to move the control variable back towards the set point in this direction. So once the disturbance goes away, the controller is going to continue to move it in this direction, and it's going to cause an overcorrection. Okay, now that we have, so the error is y set point minus, so we have this positive error here, set point minus y. And so during this time, during this time, there's going to be an overcorrection, and then as this error starts to become equal to this error, now we have also the proportional term. So for the PID controller, at this point, the proportional term is going to cause the control action to start decreasing. The integral term, the effect of the integral term is going to be less, and the controller is going to come back down to 0, and it'll get back to this set point once these errors are equal to each other. Okay, and if we look at what the controller is doing during this time period, so for this time period right here, the controller is saturated. Now the controller is going to stay saturated because what it's trying to do is it thinks it needs to further push the control variable up in this direction because it has this large error term that's been accumulated. All right, so we want to get rid of this. So we want to prevent that from having this, because once the disturbance goes away, we would like to see the system respond according to the criteria that we tune the controller to operate with. Okay, so for a while the control output is saturated, and this causes error A. So this term error A to accumulate. So after the disturbance goes away, the control output remains saturated for a while due to the accumulated error. And again, this is going to cause an overcorrection. Because again, the controller thinks it needs to continue to push up in this direction to get rid of this large error that's accumulated in the PID controller. So again, overcorrection in the control variable. So anti-reset. So our strategy for anti-reset windup is, again, here we're going to look at the same plot where we have our set point, and then there's some sort of disturbance that affects the system. So in this case, with an anti-reset windup strategy, when the manipulated variable saturates, the controller logic is going to stop changing the value of the error. So the controller logic stops changing the value of the integrated error. Okay, so at this point right here, we have saturation, so the controller is going to stop changing the value of the accumulated error. That way, for all this time period right here, so we still have some error that's been accumulated here, but all of this error no longer affects the control logic. So once the disturbance goes away, the calculated value of the C has not been corrupted. By windup, so the controller returns to the CV set point more quickly. And so what that means is now at this point, once the disturbance goes away, and we no longer have the sustained offset, right? The controller is going to behave as we've tuned it to. So we're going to have whatever the decay ratio we achieved, and we'll get back down to the set point much quicker than before, and we eliminate that overcorrection that is caused by the integral term in the need of the integral term to have that accumulated error over time be equal to 0. So there's a variety of methods that anti-reset can be incorporated. So maybe pause the video for a second and think about how might you incorporate one of these reset strategies or anti-reset windup strategies. Okay, a couple of the methods. So some of these things, and you might think about, we're not going to talk about how to actually incorporate these. A lot of times a controller will have an option to incorporate anti-reset windup. It's useful to understand what the controller is actually doing so that this isn't going to disrupt or affect your process. So some of the things, you can turn off the integral action when the valve saturates or the control loop is not in use. So to turn off the control when the valve is saturated requires a measurement of the actual valve position. So you need to know that the valve's all the way open or all the way closed. When the control loop is not in use, so for example, when you know that the select controller is controlling for a process constraint or a safety limitation, and you're not controlling based on the signal from your primary control objective, then you can have the controller stop accumulating the integral action. So that's something that it's easy to incorporate with your select controller. You can clamp the controller output to be greater than 0% and less than 100%. So again, like I said, you need to know what is in addition to knowing the actual change in controller output, you need to keep a record or a measurement of the actual controller output and use that as a way to prevent the integral term from accumulating when you're outside of those ranges. Or you can apply internal or external reset feedback, and that's beyond the scope of this textbook or this topic. Okay, so we're going to switch gears a little bit to what's called Bumpless Transfer. So Bumpless Transfer is essentially something that you can do to avoid having step changes in your set point. So Bumpless Transfer is effectively a ramp change in your set point that the controller incorporates automatically when the user applies set point changes. Okay, so when a control loop is started without Bumpless Transfer, the process can go crazy due to, again, it's going to be affected by large errors. So large errors between the set point, which is the user-defined term, and the actual CV value. So with Bumpless Transfer, an internal set point equal to the present CV value is used initially in the controller. It is then ramped slowly to the actual desired set point. Okay, so what this means is that the controller incorporates an internal set point that's different than the actual set point that's asked for by the operator. So for example, if you have a system running at 1 gallon per minute and you apply a step change to 2 gallons per minute, the controller is going to apply an internal set point that ramps the system from the 1 to 2 rather than the abrupt change. And we saw before that the abrupt change can cause large proportional terms and large derivative terms that can cause the system to misbehave or go a little bit crazy. Maybe pause and think about what were some of the other methods that we used to prevent these large step changes or large set point changes from affecting the controller. We did some digital implementation approaches that can be used as well. So how do you think those might deviate from this, or which approach do you think could be more useful or beneficial for different types of feedback control systems? Okay, so anyways, the Bumpless Transfer, this provides smooth startups and smooth transitions by essentially ramping the system. And so we'll look at on the next slide what this looks like. So when a true set point change looks like this, again, typically it's going to be a set point, so the user doesn't necessarily have to just slowly ramp it up. Your controller has an internal set point that looks like this ramp. And now during this time period, if you look at initially, this error associated with this small ramp change is going to be very small relative to the error that's the real error between what the user asks for and the actual value or the actual control variable. And so by having this ramp set point, right, the system can gradually change to the new set point without having large disturbances. So essentially it's an automatic ramp that eliminates the user from solely. And so in terms of inside the controller, there will probably be essentially a delta y set point over delta time, like a ramp user input that you could apply to the system, or other ways of incorporating this type of ramp. But again, for Bumpless Transfer, there should be a controller setting that will tell you what this is, and as the engineer who's managing the process, you should be well aware of what this type of change is, because this type of change can limit your controller performance, and we'll see what I mean here. So this slide right here shows an example of the control variable, so CV response, with and without Bumpless Transfers for set point changes. So without Bumpless Transfer, so again, let's just plot on here. Maybe there was a step change asked for by the user. So without Bumpless Transfer, what we see is that we have these large oscillations that occur in the system, and the system levels out eventually and gets to the current value. With Bumpless Transfer, instead of having this set point right here, we might maybe have this dashed set point change. And this dashed set point change, or this ramp, causes your system now to slowly change and reach the new steady state value, and it doesn't undergo these large oscillations that we saw without Bumpless Transfer. But now you can see the problem, or the difference here is that with this case right here, this is starting to look like an overdamped type of response, right? This one right here has a very high decay ratio. But remember, if we go back and we look at what's the error associated, the difference in error between these processes, in the case of without Bumpless Transfer, we likely have a lower error between the set point and the actual value, even though we have these oscillations, because the Bumpless Transfer has these large errors associated with this gradual change to the new set point. But again, if doing things like setup or process changes, it can be beneficial to have this gradual change, and the difference in the error isn't so important because you're getting to a new process position or starting your system up to get it to where you need to be without having these large changes. Okay, so the final thing we want to talk about for this video is what's called split flow control. And so in the first example we'll talk about is split range flow control. So what this is that in certain applications, a single flow control loop cannot provide accurate flow metering over the full range of operation that's required for the specific process. Okay, so in this case, we can use what's called split range flow control. This is going to use two flow controllers. One's going to have a small control valve, and one's going to have a large control valve in parallel. So at low flow rates, the large valve is closed and the small valve is used for control. So small valve is used for control. Okay, and as the flow rate needed increases, the small valve will be open. Small valve is fully open, and large valve is used for control. All right, so here's what it could look like in practice. So we have our flow entering the process. At low flow rates, this valve right here is closed, and the flow goes through the small valve only. So again, depending on what the specified value of the flow is, at low flows, measure the flow. This valve is open. Once this valve is fully open and the flow is higher, or once the valve is fully open, or for larger values of F specified, the second control valve is going to start to change, or is going to open and change to control the flow for the process. So at large flow, this valve right here is open at large flow, and then control is achieved with the second valve. Okay, this is shown on this plot right here. So this right here on the y-axis, we have the signal to the control valve versus the total flow rate. Okay, so down here at low flow, you can see that as the flow that we need increases, we have the signal to the control valve, the small control valve, is going to increase. Okay, so for low flow, we can achieve control over this range shown here. Once the small valve is fully open, so as we further need increased flow, now this valve is going to be 100% open up here, and then the large valve is now going to start to open. So down here, the large valve is going to open. So the large valve is going to open and close to achieve the flow rate, within the larger flow control range, while the small valve is already fully open. Okay, there are other reasons why we might use two control valves for a given system, and so this is an example of split range temperature control. So for split range temperature control, you could have a reactor system that might require both cooling water and steam. So for example, think about a reaction. What type of reaction? So probably an exothermic reaction. So for an exothermic reaction, we probably need steam to heat up the reaction to the target temperature to get the reaction going. Once the reaction is going, we will use cooling water to remove the excess heat generated by the reaction. So again, if the system quenches or cools down, we can use steam to heat it up to keep it at the target temperature, cooling water to remove the heat generated or released by the reaction. So maybe take a minute, think about how would you actually implement this. Okay, so how split range temperature control works is shown here. Okay, so this plot right here shows the signal to the control valve as a function of error from the set point for the jacket temperature, and it shows it for two valves. This valve is for the cooling water, and this valve over here for the steam. So let's recall that the error in this process is going to be T specified, so the specified temperature value minus the sense value Ts. Okay, so when we start up the system, right, when the system is just starting out, maybe the temperature being sensed is about 25, and let's just say our reaction specified value is 100 degrees C. That's where we want it to occur. Okay, in this case right here, we have a large positive error. So this would be a large positive error. In this case, the steam valve is going to be nearly fully open. It's going to be open to cause the system to heat up. As the system heats up, the error between the system and the set point is going to decrease, and as the error between the set point and the sense value decreases, the amount of steam needed is going to decrease, so the valve position on the steam is going to close. And then at some point, we're going to no longer need to heat the system, so the steam valve will close. Okay, at this point, when the reaction's at its target temperature, the reaction temperature is going to continue to heat up. Okay, so as the reaction heats up, as the reaction continues to heat up, the cooling valve is going to need to turn on. Okay, so at some point the cooling water will turn on to start cooling the system down. So again, the error in this point, once we cross this line, we'll have a negative error because the system, it heats up from the steam, and then the temperature continues to increase due to the reaction being generated, which is going to cause a negative error. So at some point over here, the T sensed as a function of T is going to be greater than T specified. And when T sensed is greater than T specified, this is going to be negative error. The cooling water will turn on. So the larger the negative error, the more the cooling water that's going to need. And then at some point, the system will settle on at what it's, the steady state value. So because it's an exothermic reaction, we can assume probably the steady state value will be somewhere where the cooling water is turned on because the reaction is generating heat, the cooling water is removing heat. We want to keep it at a target temperature. Okay, so this shows an example of how split range temperature control can be used to both heat up and control the temperature for at least an exothermic reaction. Okay, so as an overview, we discussed a few things. So all controllers that employ integral action should have anti-reset windup applied. Okay, so remember, not all controllers have to be PID. We could have proportional only controllers. Remember, that would be for like an integrating process or a non-self-regulating process. Bumpless transfer provides a mean for smooth startup and also provides a mean for smooth transitions between desired operating set points. And then also for maybe systems that require both heating and cooling or large flow ranges, we can use split flow control to achieve improved control in a given process. Okay, so that's going to do it for today. We'll stop there and we'll see you next time.